Hello students, this is our next lecture, and in our last session we have discussed about the critical section and the solution to the critical section, and we have seen how can we provide the solution to the critical section problem using the software based solution. The name of the solution was the Peterson solution. We tried to attain the solution to CS problem by satisfying all three criteria, namely mutual exclusion, bounded weighting, and the progress. So today we are going to talk about the another type of solution for critical section problem, that is solution hardware and the semaphore, right? So we'll start with the synchronization hardware. So basically, from our last session, we have understood that in order to have a solution to the CS problem, all three criteria has to be satisfied, namely mutual exclusion, progress, and bounded weighting. So there are many systems that has the ability to use the hardware for finding the for providing the solution to the critical section problem, and that hardware we are going to discuss in this topic, that is synchronization hardware. So synchronization hardware tries to provide the solution to the critical problem by use of hardware in the computer system. They basically use the atomic operation, and atomic operation I've already covered in my previous session. So basically, just a recap, atomic operations are operations which cannot be preempted once the instruction starts to execute, right? So in this synchronization hardware, they try to provide a solution by using the hardware, and that hardware, the instruction that execute on the hardware are atomic operations which cannot be preempted in between, right? So they try to use the two type of instruction. One is for test and set, and the one is for swap. Okay, test and set means you will receive one the hardware. This hardware will execute this code. Hardware will receive one information, okay, of boolean variable, and check the boolean variable and then return true value. Okay, so the main outline of the test and set is this, as you can see in this diagram. Sorry, in flowchart. Sorry, algorithm. Okay, so it will try to check the it will try to check whether it can acquire a lock or not. Once, because if it has to enter a critical section, it has to acquire a lock and then only enter into the critical section. Now the importance of acquiring a lock is to not to allow other process to execute the critical section, because the current process is executing it. So it's kind of you can assume there is a room. Okay, you want to do some task inside the room privately, and you go to the room and you don't want to get disturbed, so you enter the room and then lock it. Okay, and then you do a task, and whenever the task is completed, you just come out of it by unlocking it. So that is the same idea out here. Okay, but the instruction is run on the hardware. So this is the instruction sent to the hardware test and set. So it will try to check it, okay, whether it is locked or not. Only if it is unlocked, then it will enter the critical section for executing the critical section code. If this condition is true, then it will remain in the while loop. Okay, so just like this pin lock, which we have already covered in our last session. And the last and after the critical section code is executed, it will try to unlock it and then execute the remainder section. So this is what the how the test and set instruction work. Briefly, I am discussing. Now next is the swap instruction. Swap instruction. So this swap instruction is given to the hardware, and hardware will swap the values of the A and B boolean variable. So how it will work? So as I've told you already, that the idea is very same as that we have discussed. So we'll have an entry section code. These are the two, the entry section code or the lock acquiring code. Okay, if this condition is true, okay, it will do this task, and if the condition is false, it will execute the critical section, and after completing executing the critical section, it will unlock it and then come out of the critical section and execute the remainder portion of the code, right? Now, semaphore is also an solution to the critical section problem. So it will work for more than one process. Okay. So rather than speaking on that, I'd like to directly continue on what is semaphore. So basically, semaphore is a synchronization tool. Okay, that will help in finding out the solution to the critical section problem. In most of these our example, we will discuss about the two process. So as we have seen in our previous session, like algorithm 1, algorithm 2, or algorithm 3, most of the time when what was happening is that when one of the process pi was executing the critical section, the other process was continuously executing the while loop, checking the while loop, indicating that okay, whether the condition has been successfully, whether the condition is true or false. If the condition is true, then it was stuck in the while loop. If the condition is false, then the continuously checking process was able to enter the critical section. So there is something called busy wait over there, or spin lock. Okay, so this is not good about the, because it wastes some of the CPU cycle. So basically semaphore is a synchronization tool that will try to provide a solution without busy wait, okay. So we'll discuss over some time, after some time, how without busy wait it try to solve the problem. So if we talk about the definition, semaphore is basically an integer variable. Okay, semaphore is basically integer variable, and this integer variable updation, okay, this integer variable updation is basically done by the two atomic operation, wait and signal. The instruction for the implementation of wait and signal is over here. So wait will basically decrement the semaphore value by 1, and signal will increment the semaphore value by 1. Okay, so increment and decrement. Okay, so increment corresponds to signal and decrement corresponds to wait. Okay. So these two, wait and signal, although you can see there are a few lines of code, here we are assuming that it is an atomic operation. It is an atomic operation means whenever the computer system is executing wait or signal code, it cannot be preempted in between. Okay. So this is the implementation of the wait and signal. So now let us see the different types of the semaphore. There are basically two different kinds of the semaphore: counting and binary. Counting semaphore is basically an integer value, okay, or the type of the semaphore which takes input as some integer. Okay, now that integer is equal to the amount of resources that we'll be going to use. Suppose there are 5 printers associated or connected with the computer, so the resources will be 5. Okay, printer resources will be 5. So if you are working with the sharing of these resources, so counting semaphore will be initialized with integer value 5 because the number of printer were 5. So this is just an example. So basically counting semaphore keep track of resources, number of resources available in the system, right? Now whenever there is a use of some resources, there will be updation in the counting semaphore. You will be more understanding about the counting semaphore in upcoming examples. Now next is the binary semaphore. The main objective of using the binary semaphore is to acquire a mutex. Okay, mutex is basically a short term for mutual exclusion. MUT stands for mutual, EX stands for exclusion. So mutex stands for mutual exclusion. Okay. Now, now binary semaphore. Basically reads some integer value, and the value ranges from 0 to 1. And this type of semaphore is basically used to acquire a lock. Okay, or used to generally acquire a mutual exclusion property. So So basically, whenever anybody wants to enter into critical section, it will try to change, update the value of binary semaphore and then enter the critical section. And after executing the critical section code, while coming out of the critical section code, it will execute the or update the value of binary semaphore to release the lock. So acquiring and releasing locks is accomplished using the binary semaphore. Okay. So next is like uh, how busy wait and all we'll be discussing. Okay. So initially semaphore will be initialized with some value, and based on this situations, wait and signal will be invoked. Okay. Like for example, whether irrespective of whether it is a binary or counting semaphore, suppose you are writing or trying to implement a semaphore. So idea is you will have a semaphore which will have some initial predefined value, and then you will wait. You will wait means you will try to see if any other process is executing the critical section or not. If it is executing, then it will stop in this loop. Okay, it will stop in this loop, or it will not execute, or it will not enter the critical section. If none of the process is executing critical section, then this condition will become false, and then the requesting process will be allowed to enter the critical section. After completing the code written in the after completing the execution of critical section code, it will execute the signal. So wait and signal is a pairwise atomic operation before and after entering the critical section respectively. So whenever you want to enter the critical section, wait has to be invoked first. Okay, after completing the execution of critical section code, signal has to be written over there. Okay, fine. Okay, now next is okay, semaphore implementation. So now how we implement a semaphore. Okay, so the code for wait and signal has been already informed to you. So semaphore implementation can be of two types, one with the busy wait and another one is the without busy wait. So with busy wait, we have already seen a similar kind of example in our Peterson solution. So like that way, what will happen out here is that in the busy wait, the suppose this is one process, similar code will be there with another process. If one process is busy executing critical section, the another process will be stuck in the wait code, which has further while loop. Okay, while s is less than equal to 0. So in that while loop, it is continuously checking it. Okay, so basically it is trying to use the CPU cycle in that while loop. Okay? So however, we are interested in identifying the semaphore implementation or understanding the semaphore implementation without a busy wait. Okay? So what is happening out here is that whenever a process is checking, whenever a process has to wait, because whenever a process has to wait for entering the critical section because some other process is executing it. Okay, then what happens is that without for no busy wait, suppose there is a process P1 and P2, and P2 is executing the critical section. Now P1 will be in this wait atomic instruction. So what will happen is that P1 has to wait. So instead of while, what will happen, it will check the value. Okay, it will check the value. If the value is negative, it will, if the value negative means this P1 process is not allowed to enter the critical section. So in that situation, what will happen is that you will add the process P1 in the linked list. Okay, it's queue. Okay, in the linked list. Okay, and then we block that process so that there is no continuous checking. There is no continuous checking. Please note down out here, the implementation of wait instruction over here is not the while loop, rather than it's a if instruction. Okay, so for the one time it is checking. If it is not allowed to enter the critical section, it will put the list, it will put the assign the process in the waiting queue or in the queue, and try to invoke the block system call so that it will try to sleep. Okay, block or sleep, it means the same thing. Sometimes we call it as a sleep also. Okay, block or sleep both means the same thing. Now once the process enter into sleep mode, it will not keep on checking the its criteria, right? So now how the process will able to know that when that P1 will get chance. So that is basically identified with the help of the signal code. Whenever there is whenever there is no other process executing the critical section, and there is some process in the queue who is interested in the executing the critical section, then what happens is that a signal code will be invoked, wherein the value of the value will be checked. So say for example in the queue, okay, queue is last in first out. So last in first out, or whatever is the scenario, whichever node or whichever process is eligible for executing critical section or interested for executing critical section, that value will be checked, and then that process will be removed from the queue and will invoke the wake up. Okay, so we'll invoke the, initially we have invoked the select, now we have invoked the wake up. So wake up means now you can enter the critical section. So that's how you implement the mm, block and wake up system call for implementing the semaphore with no busy wait. Now this queue, add this process to waiting queue, remove the process P from waiting queue, is implemented with the help of the linked list. I hope all of you are well versed with the data structure linked list chapter, which you have already covered in your third semester. Okay, so with the help of the block and wake up system call, you can implement this semaphore without uh, busy wait, right? Okay. So now next topic is this is very small topic, deadlock. Okay. Now for deadlock, I'd like to give you one small example. Right? Suppose there is a process. Okay, suppose there is a process, and name of the process is A, and there is another process B, and there are many lines of instruction inside this A code and B code. Okay, and somewhere in between, okay, of both A and B code, they want resource. Okay, they want resource. So this resource could be a printer. Okay, this resource could be a printer or memory, shared memory, or anything else. Okay, that is being shared. Now suppose this process, there are two resources. Okay, there are two resources. I will assume that there are two resources, R1 and R2. Okay, now R1 and R2. To completely execute all the instruction of A, it needs both R1 and R2, and similarly to completely execute all the instruction of B, it needs both R1 and R2 resource. Okay, now at certain point of time, maybe at T1, okay, suppose R1 is assigned to A and R2 is assigned to or is allocated to B. Now A, while holding resource R1, is waiting for resource R2. Okay, and similarly B, while holding the resource R2, is waiting for resource R1 when it will be allocated, when it will be released and allocated. Now this kind of situation is known as a deadlock situation, wherein a process is holding one resource and waiting for another resource, and that resource is held by another resource, sorry, another process, and waiting for the resource that is held by the other process. So this is a deadlock situation. So that's what I want to display, convey out here. Deadlock, when two or more processes are waiting indefinitely for an event that can be caused by only one of the waiting process. So basically what is happening out here, that A is thinking that B will release this R1, okay, and so that it can execute, but again B is thinking that A will be releasing R2 so that I can use it and complete my task. So this waiting will go indefinitely. So this situation is known as a deadlock. We have a separate chapter on it in the next chapter, right? So next is the starvation. So starvation is something like indefinite blocking, okay? Something which cannot be whose situation cannot be deadlock cannot be removed for infinite amount of time. That is known as starvation. Or in other words, Say for example, I'd like to give you one more example for starvation. Suppose there is a process. Okay, suppose there is a process A. Okay, and there is another process B, and there is another process C. Dot 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 dot. There is n number of process, n number of process. Okay, now it may happen that different process have different priority, 1 2 3 4, right? So what will happen is that whenever during the execution of the processes, there may be lot of process coming in and going out of it. Okay, so every time a process is coming, it is preempting the low priority. Suppose this process is a process with minimum priority. So every time a new process is arriving in the system with some priority, and that priority is higher than or greater than this process. So in that case, what will happen? This process will never get a chance. Okay, this process will never get a chance. So this leads to a problem of starvation. So process N will starve for resource because somebody is preempting it. Okay? This is all due to the starvation. So now we will see some of the classical problems of synchronization, uh, wherein we'll try to provide the solution to it. So in today's session we'll only talk about the bounded buffer. Reader, writer, and dining philosopher will be discussing some other classes. So bounded buffer means, in case of bounded buffer, there is a limited resource. Say for example, the resource is memory. So there is a memory where you can store the information, and the size of the memory is limited in size. Maybe only 10 cells are there, or only 100 cells are there. So in that limited resource space, you need to store your data. So it is very obvious that uh, in this limited space you cannot store the data for infinite amount of time. Okay, so, or in other words, I'll give you example. Suppose there is a resource memory, and in this resource there are three memory cells wherein you can store each data. Suppose this is first data, second data, and third data. Okay, now if you want to store the fourth data, but you can't store it because there is no space. Okay, now if you try to store it, what will happen? This data will be lost. Okay, so this is the problem that is faced by the bounded buffer. Since the resource is limited, so how you will try to store this 4 without in a synchronized fashion, so that is discussed in the bounded buffer problem. Okay, so bounded buffer problem is the example of bounded buffer problem is the producer consumer problem. So typical example of bounded buffer problem is the producer consumer problem. So in this problem, the definition problem is this: there is a two process. One is the producer process, and another one is the consumer process. Okay, so there is something wrong over here. Okay, I'll just correct it. Yeah. So the typical, I'll just repeat it. Typical bounded buffer problem is the producer consumer problem. It is a very famous problem of synchronization, wherein there are two processes: producer process and the consumer process, right? So I'll explain this with the help of the example. Suppose there is a two process. Okay, so this is the producer process and this is the consumer process, and just hold on, and there is a bounded buffer. Okay, so there is a buffer which is limited in size. Okay, so the job of the producer is to produce the item. So it produces the item and store it into the memory. Okay, so it will go here. Again, the job of the consumer process is to consume this item. Okay, remove this item from the buffer and consume it. I repeat, the producer will do two tasks. It will produce the item and initialize in the buffer, and consumer will remove the item from the buffer and consume it. So this is the basic architecture of the producer consumer problem. So problem is this: producer will always produce the item and consumer will always consume the item. And synchronization, the problem is you need to synchronize these two processes in such a way that no informations are overfilled. Overfilled means no informations are lost. Thus, whenever a producer produces any item or whenever produces any information, there should be always or at least one space in the buffer where you can store it. And whenever consumer process try to consume the item from the buffer, there should be at least one item in the buffer for it to consume it. So this synchronization task has to be accomplished. I repeat, synchronization task is whenever producer produces an item, there should be at least one free space in the buffer, and whenever consumer consumes the item, tries to consume the item from the buffer, there should be at least one item, consumable item, that should be available in the buffer. Okay, so this code is the solution, but before that we'll see some of the our assumptions. So for example, we have got the buffer of n size. So the number of space in our this example there were only 3, but here to generalize the situation there are n number of buffers where each buffer can hold one item. Okay, each buffer can hold one item. Now next is the there is a semaphore. Semaphore is basically a shared variable and integer variable, which producer and consumer both can access it, and it's an integer variable. So the updation of this semaphore is basically, or not basically, always done with the help of the two atomic operation wait and signal. The general syntax I have already shown you. Whenever any process want to execute the critical section, it has to first invoke the wait and then enter into the critical section. While coming out, it need to invoke or execute the signal atomic operation. So wait and signal basically wait and signal instruction basically works on the semaphore only. So these are the 3 different semaphore that is used in the bounded buffer and producer consumer problem. So first semaphore is mutex. As I already told you that mutex stands for mutual exclusion, and this semaphore is basically used to attain or to achieve mutual exclusion property for synchronization, right? So there is a semaphore mutex, name of the variable is mutex, which is initially initialized to value 1. Okay, which is initially initialized to value 1. And there is another semaphore full. This full semaphore is basically initialized to 0. It keeps track of how many number of how many number of items are present in the buffer. So if the value of full is 5, then in the n buffer 5 items are filled. Okay, so full semaphore tries to keep track of how many number of items are filled in the buffer. Next is the semaphore empty. Okay, so its empty semaphore is basically tries to keep track of how many number of empty buffers are there. Okay, how many number of empty buffers are there. So let me give you an example for the same. Suppose there is a 3 buffer, so n here is equals to 3. So initially full will be 0 because you have not filled any item, and empty will be n. So n here is 3, so 3. Okay, so initially there is 0 item in the buffer, so full will be 0, and number of empty space is 3. Okay, so say for example at particular time you have a producer that produces item A. So it has produces item A and it is initialized. So now what will be the update? So full will be 1. Okay, so 1 item is full. It keep full semaphore keep track of how many number of items are there in the buffer. Okay, empty how many number of free items. So there are one item in the buffer and two free space are there, in the buffer. So this is how you need to interpret, right? Now, so this is the code for producer. So producer will produce an item. So you can, for producing the item, you might be thinking like, how do I implement it? You can use a random function, RAND function in Ubuntu, or many compiler. It supports random function. Okay, so it produces the item, and after producing item, it will try to see whether it can initialize in the buffer or not. But before that, it needs to check whether somebody is in the critical section or not. Okay. So it tries to check the empty. So basically, when this statement wait empty is executed, it is basically trying to understand that is there at least one empty space in the buffer. If yes, then it will again execute mutex for locking it and then add that item to the buffer. But if there is no free item, sorry, if there is no free space, if there is no free space in the buffer, then it will be stuck in this semaphore itself. Okay, maybe semaphore, if we talk about the busy wait, so semaphore will be busy wait, so it will stuck in the while loop. Okay, so this is how it is done. Okay, now suppose I am assuming that there is at least one free space in the buffer, so this will be false, so it will go to this. Okay, it will unlock it, sorry, it will lock it, lock it, and then assign the item into the buffer, and it will change the value of mutex, unlock it, and then increment the full. See, you need to wait, you're decrementing the wait empty. So empty keeps track of how many number of empty space, okay, and full keeps track how many number of full. Since I've added item into the buffer, so full has to be incremented by 1. Okay, so this is how producer works. Now let us see from the consumer point of view. So consumer means you retrieve the data from the buffer and destroy it or consume it. So you need to check if you want to consume any item from the buffer, you need to check whether there is at least one item in the buffer for me to consume or not. If there is at least one item, means this condition will be confirmed. Then it will get lock it and then remove the item from the buffer, and then change the value of these two semaphore and then consume. So this is how producer and consumer works. I hope I had made it clear. So this is same code. If there is any questions, please post it out. Okay, so now before I end up the session, I'd like to give you a brief idea about, from the implementation point of view, how you need to execute the code, right? So because I'll be not coming up the online in the lab session, so that's why. So let me give you a scenario, generalized scenario, whether it is a Peterson solution or whether it is a producer consumer problem. You will have two separate program. Okay, you will have two separate program. Say for example, p.c means producer.c. okay, and there is another C file, c.c, consumer code.c. okay. So there are some instruction. Okay, there are some instruction. Now this things has to be executed in two terminals. So this is in terminal 1, and this has to be in terminal 2. This has to be in terminal 2. Okay, so Ubuntu will be the best suitable platform where you can implement the synchronization problem. So T1 and T2, right? T1 and T2. See, when you write down the proper code and you give the command gcc and ./a.out, since it is in the while loop, it is keep on infinitely executing it, and here also it will infinitely execute it. Now, when you see the output of these two, producer consumer or Peterson solution P1 and P2, both of them will always try to synchronize in such a way that they are trying to access the shared variable or shared memory only one at the same time. Okay, so that's all for today. I hope I made it clear. If there's any question, you will post it out, and we'll have a discussion on it same in the further upcoming session. Thank you so much.